In the last video, we learned how fatty acyl-CoA was transported out from the cytosol into the mitochondrial matrix, which is where beta oxidation occurs. And now we're going to go through the whole process of beta oxidation. So this is just continuing on from that first stage where we have to transport the fatty acyl-CoA into the mitochondrial matrix. But then what happens? So in the first step, fatty acyl-CoA is converted to a fatty acyl-CoA with a double bond between the alpha and beta carbons of the fatty acyl group. Now, when we label compounds, alpha is the first carbon that is away from the functional group. So that's how we label the carbons. So you label it based on how far away they are from the functional group. In the case of a fatty acid, it's a COOH group. So it goes alpha, beta, then gamma. So that's why we're labeling them in this way. So we've got a fatty acyl-CoA with a double bond between the alpha and beta carbons of the fatty acyl group. But from a biological chemistry perspective, I probably wouldn't go through and draw out the whole chemical formulas and try and wrap your head around all the different structures. I would just understand the process because, yeah, from a biological chemistry point of view, you're probably not going to need to know all of the complex chemistry behind it. So now we know that we've got simply a fatty acyl-CoA going to a fatty acyl-CoA with a double bond. So the basic part of this is it's oxidation step 1. We've got a formation of a double bond, and in this process an FAD is converted to an FADH2. Instantly you should be thinking there must be a dehydrogenase involved, and in this case it's acyl-CoA dehydrogenase that catalyzes this step. So now that we have this fatty acyl-CoA with a double bond, we move on to the next step, which is the hydration step. As you see, we add water in here. So we remove the double bond. So in the last step, we formed a double bond, now we're going to remove it. It seems a bit weird that you've got to form it and then remove it, but that's just how the process is. And as I say many times with biological chemistry, sometimes you just have to accept that that's just the process and that's how it goes. There's not always a very solid reason to it. So enoyl-CoA hydratase is the enzyme here. So the fatty acyl-CoA with a double bond becomes a fatty acyl-CoA plus a water. So a hydrogen ion is added to the alpha carbon and a hydroxyl group, which is an OH group, is added to the beta carbon. And the double bond is removed. That's the key parts of this step. I would just commit that to memory. Writing it out a few times should do the trick. The next step is oxidation step 2. So we formed a double bond, then we removed a double bond. Now we're going to form a carbonyl group, which is a double bonded oxygen. So an NAD is converted to an NADH. Again, you should be thinking dehydrogenase must be involved. And in this case, it's beta-hydroxyacyl-CoA dehydrogenase. And what we form is we remove the double bond in the last step, and now we're going to form a carbonyl group. So we form a fatty acyl-CoA with a carbonyl, which is a double bonded oxygen group, on the beta carbon. And that's where it's located. And that's why it's called beta oxidation, because we're really working on that beta carbon to break down the fatty acid. In the final step, a HS-CoA or a CoASH, so that's just a molecule that is used in this reaction. So it's called the thiolytic reaction. So we add a CoA and we form acetyl-CoA. And the enzyme here is beta-ketothiolase. And the final step is that this CoASH or HS-CoA, you'll see it written either way, reacts with the beta carbon. Again, remember that's why it's called beta oxidation, on the fatty acyl-CoA. And then we form an acetyl-CoA and a fatty acyl-CoA that is 2 carbons shorter than the original fatty acyl-CoA. So we've got palmitate, which we discussed as an example of a fatty acyl-CoA. So we've got 16 carbons, and each time we go through, we're removing 2. So we kind of remove 2, we remove 2, and then we remove 2, remove 2. So we remove 2 until we get to the end, and that's why I've drawn this red dotted line. So at the red dotted line, what's going on? So let's think of what happens at the end. So I've written it out here so you can help you to understand what's going on. So the shortened fatty acyl CoA, so one that's got 2 carbons removed, returns to oxidation step 1. So it goes back up to oxidation step 1. It's not quite in the frame, but there it is. It goes back up here. And then it goes through the other steps. And it releases acetyl-CoA at the end of the cycle each time. So because acetyl-CoA has 2 carbons. And then the process is repeated until you get a 4-carbon fatty acyl CoA, which is produced, and then that is split that's split in half at this dotted line with the addition of a CoA to produce 2 acetyl CoAs. Might need to watch that again to make a bit more sense, but I recommend just drawing it out like this and then crossing off 2 carbons that represent the acetyl CoA each time you go through, and then you can just move the remaining chain up there and then go through the other steps and then remove another 2 for acetyl CoA and keep going through. And if you do that a few times, it should help you understand the process. The most important part about this process though is how much ATP are we generating. So I've written here that 1 acetyl CoA is 10 ATPs, and we know this from the TCA cycle because 2 acetyl CoAs in the TCA cycle make 20 ATPs all up, and if we divide that by 2, 1 acetyl CoA will get you 10 ATPs. So let's do an ATP calculation. For example, for palmitoyl CoA, which has 16 carbons and no double bonds. So what we're going to do is we're going to recall that an FADH equals 1.5 ATPs and an NADH equals 2.5 ATPs. And now we're going to go through the total number of ATP. So what I do is I count how many FADH there are. So there's 7. And you can see that because we've got our 16 carbons here. So we've got 1, 2, 3, 4, 5, 6, 7 times. So it's going to go through the steps 7 times. So we're going to have 7 FADHs. It's going to go through that first step that we saw right at the top here 7 times, as we've drawn here. Because in the final step, that last, in the 4 carbons that are left in the final step, they just break off into 2 and they become acetyl CoAs with the addition of a CoA. So then the same goes for NADH. So NADH is worth 2.5 carbons. So we're going to go through the step here, oxidation step 2, 7 times because 1, 2, 3, 4, 5, 6, 7, and then at the end we just break it off. So we're going to go through that step 7 times, and finally we're going to get 8 acetyl CoAs produced. 1, 2, 3, 4, 5, 6, 7, 8. So we've got our 16 carbons, 16 divided by 2 is 8. We've got 8 acetyl CoAs produced at the end. So we're going to times that by 10 though, because as I said before, 1 acetyl CoA equals 10 ATPs. And we know that from the TCA cycle. Now we've got to recall that there's 2 ATPs used at the start. You can look at the other video about how fatty acyl CoA is transported into the mitochondrial matrix. So right at the start we had 2 ATPs that were used. So therefore the number of ATP that is produced, so after I did that calculation on my calculator, I got 108 ATP. So we've got to take away 2 from 108. So the total number of ATPs produced is 106. And you can repeat the same process that we just did for any other fatty acid of varying carbons, but just ensure that they're even, because this was explaining beta oxidation for fatty acids with an even number of carbons. And now you can calculate the ATP. And I would think that calculating ATP is a really important part of this process because that shows that you understand what's happening in beta oxidation. So that is the basics of beta oxidation. So that's beta oxidation with an even number of carbons. And in the next video, I'm going to look at special beta oxidation cases. So we've looked at it with saturated fatty acids, so those are ones that don't have double bonds, but then you can also have special cases where you can have unsaturated fatty acids with double bonds and odd numbered fatty acids that go through beta oxidation. So we looked particularly at ones with even carbons and ones that are saturated, but we're also going to look at some special cases a bit later. But yes, that was the basics of beta oxidation.